Hey guys, welcome back. This is the part 6 in case of a MIMO OFDM series. Okay, so please go through the series. So there is a separate playlist. In this video, I will be mainly talking about the MIMO MMSE equalization. Okay, so in case of OFDM, we do the equalization in frequency domain. So even we call it as frequency domain equalization (FDEQ). Okay, there will be FDEQ block. So far we have seen many other equalization techniques like the zero forcing equalization and MRC and all, right. So in those cases, what we have assumed is that x bar, which is an unknown quantity, is a fixed quantity, basically, which means that it is not a random quantity. So this is our system model. Okay, but from now onwards, we can consider x bar as random, and this is true in our case, right? Because x bar is a data, and data could be random, 1010 and things like that. And from 1010 random bits, we are going to actually convert it into a random complex number, right? So the thing is that we have some information available about this x bar. Okay, that is the prior distribution of x bar. If we know that, then we can utilize that information and we can do much better estimate. Okay, in the previous video related to zero forcing equalization, we had not considered any distribution about x bar. We had just considered that x bar is just a fixed quantity, right? So to be to come up with a more optimal estimation, if we know the prior distribution of x bar, then we can get a more optimal estimation, and that is what is called as a Bayesian estimation. Okay, so let us see what is the prior information we have, what is that we need to consider and all as part of a Bayesian estimation. But I want to talk about some basic concepts about the Bayesian estimation, and how the Bayesian estimator would look like, and then we will go on to the one which we are going to use in our practical system. So basically, the Bayesian estimation, let me consider the mean square error of it. So since our model is y bar is equal to h x bar plus n bar, the mean square error would look like this. Okay, since x bar is now the random quantity, we need to consider the expectation, and x bar is I am considering it as a vector. That's why we need to take the norm square. Okay, but to simplify this, let's say I will consider the scalar version of it. Then it would become like this, and for which the formula can be written as shown here. Okay, so I've just used the expectation formula and I've written here. What is this? This is nothing but the probability of y bar parameterized by x. Okay, this is some notation based on the estimation theory. Not to worry, I am not going through the derivation of all these things, but I want to say that from here, if you apply uh, base theorem. Okay, some base theorem, and if you try to minimize, basically we need to minimize the mean square error, right? So if you try to minimize this particular quantity, in which case you need to do a partial derivative and equate it to zero. If you do that, finally you will arrive, okay, you will arrive the equation of Bayesian estimation as shown in this slide. Okay, so we will get the final expression like this. This talks about a posteriori probability. Okay, so this is nothing but the conditional density of x given y bar. So if I want to write in terms of expectation, this can be written like this. Okay, this is the final formula for optimal Bayesian estimation, since we had considered the mean square error and which we minimized it. Okay, so this is also called as MMSE estimation. So this requires the prior information of x, right, as I was telling. So, and one more point is that this x and y bar can have any distribution. Okay, but what is the prior information which we need to have? It could be the first order statistics, just expectation of x, or expectation of x square, which is a second order statistics and things like that. So based on the distribution of x and y bar, the optimal MMSE will be of two category. One is some estimator could lead to a linear estimator, some estimator could lead to non-linear estimator. This also we will try to see under what scenario it will be linear and in what scenario it will be non-linear. Okay. So with this, I want to go for the MMSE receiver. Okay. So in case of MMSE receiver, to keep the things simple, what I would do is I will just consider this as r cross 1, and I have just only one scalar quantity. This is 1 cross 1. Okay. So afterwards we will try to see how to apply this to MIMO. So based on that, the equations are derived, and even this particular formula is considered, which this is the mean square error formula. Okay, and now this x hat is considered as like this. See, the thing is, when it comes to practical scenario, right? Uh, we cannot implement non-linear estimators. I mean, we can implement, but the thing is that they will take a lot of time to uh, get the output. So, what we usually implement in our practical system is linear MMSE estimators. Okay. So, for that reason, my estimate, okay, x bar should be taken as a linear combination. Okay, so it is considered as like this. So y bar, we have y bar r cross 1 samples. We need to combine all these y1 y2 till yr linearly with some weight. Okay, that weight I am considering it as c here. Okay, then I would get like this. So this is the quantity which we need to minimize, and basically we need to figure out what is this C, right? That is what we are looking for. Uh, so to do that one, the derivation goes like this. So I have expanded this particular term, and if I expand, I would get like this. Okay, I'm not going through the explanation of this. Maybe you can go through this. If you have any doubt, you can post it in the comments. Then from here, if I want to get this is just a mean square error, right? From here, I need to get the minimum value, okay? And I need to get C bar as the argument. So then I need to differentiate this particular equation with the C bar, and I should equate to 0. So if I do that, I will get this particular quantity, and I will get back my, I will get my C. So this is the weight or the MMSE estimator equation which I am supposed to use, but this is still we can expand this, and we can utilize much more information that I will come in the next slide. But I think you finally got the equation for LMMSE estimator. Okay, this is the one. So now since this is derived, now we can expand, I mean we can take it to the MIMO case. Okay, so this is a MIMO system. So how can I apply to the MIMO system? So the same model is considered. In this case, I am taking the expectation of n bar emission as white noise. Okay, so this is pretty much important here. I'm considering it as white, and I am not considering any interference here right now, right? So that's why it is just identity, and the prior information related to x bar is considered here. Okay, for our Bayesian estimation, that is given by p of I t cross t. This is nothing but the transmitted symbols are independent across the antennas. All right, with this prior information, right now I'm not telling anything about the distribution, whether the x is Gaussian, or whether n is Gaussian or things like that, but I'm only stating the second order statistics of the noise and x bar. So based on that, Now I will calculate this RYY, okay, RYY and RXY. So, so RYY is expectation of YY emission, that will become something like this, and RXY will become like this. So if I substitute, I will get the MIMO MMSE estimator. Okay. So now having this equation, note that this is there is a matrix inversion here. This is R cross R. Usually in our practical system, R will be greater than T, right? Number of receive antenna will be greater than T. So let's say this is 4 and this is 2. Then you need to do 4 cross 4 matrix inversion, and that's where the implementation becomes very tricky and very complex. So we need to figure out a way to actually implement this particular matrix inversion in a better way. Okay, in our practical system, that is one challenging thing. Many companies would implement many algorithms, many proprietary algorithms to implement this particular inversion. Okay. Now, since since 4 plus 4 is going to be the time consuming one, and it takes more time to do the matrix inversion, there is a way to actually do some alteration in the equation, okay, something like this, and we can apply a matrix inversion. Okay, Woodbury's identity we can use, and we can arrive at the another form of MIMO MMSE estimator, which is this. So in this equation, if you clearly see, it is T cross T. Okay, whatever matrix inversion is there, that is just T cross T. In our case, which will be 2 cross 2. Okay, so which means that rather than performing 4 cross 4 matrix inversion um, in here, the same equation can be rewritten in this form, okay, in this form, and this can perform 2 cross 2 matrix inversion. This is possible, and that's how this kind of equations are used in our practical systems. Okay, um, but note that here this was possible because of the main assumption that there is no interference. Okay, and the expectation of NN emission is just an identity. All right, so let us see in the next video, if this is not identity, then what will happen to these two equations. So I think you got the two versions of equations. One is the one will take 4 cross 4 matrix inversion, another one is simpler, which is 2 cross 2 matrix inversion. All right, so let us take a condition, when there is only one TX antenna, okay, and where you can transmit only one symbol in. If you take that and if you try to simplify the MMSE equation, you will get like this. Okay, this is nothing but your MRC. So if someone asked in the interview that, okay, when would the MMSE would reduce to MRC, then you can quote this particular situation, and you can say that this is how it reduces to MRC. But when would it reduce to zero forcing receiver? Zero forcing we had discussed in the previous videos, right? So zero forcing was more effective when the SNR is very high, when there is low noise. Otherwise, it would enhance the noise, right? So at very high SNR, you can see that in this equation, this particular term will become much smaller. Okay, see here sigma square is there. SNR is very high, means noise is very low, and this is low, and this will make the upper end, and that's how you will get. Um, that's how you will get this particular equation, and this is equivalent to your zero forcing receiver. Okay, MMSC will reduce to zero forcing receiver at very high SNR. Both of them will become optimal. All right, I think you got the clarity. Now I want to talk about some more information related to MMSC here. So right now we have derived some expression, right? Um, okay, let me write that one. X bar at is equal to basically Rxy Ryy whole inverse into y bar. So this is as I was telling, this we had arrived considering the linear combination, right? That C bar transpose into Y bar. So we had taken the linear estimator. So this is a LMMSE. This is linear MMSE equation. So I was telling that in MMSE there are two clauses. Okay, one is linear and another one is non-linear. So among the class of linear, this is the optimal one. Okay, this is the optimal one. And here I had not assumed any distribution about y bar and x bar. So this can be any distribution. Okay. Now, usually in our practical system, what do we consider? Like we consider both of them, and even in noise, right? We consider them as Gaussian. In which case, even this y bar and x bar will become jointly Gaussian. If that is the case, okay, if those two are jointly Gaussian, because what is my MMSE? Just MMSE or Bayesian at the top level. So that is nothing but my estimate x bar at is nothing but expectation of x bar given y bar, right? So here the mutual distribution matters a lot. So if x bar and y bar are jointly Gaussian, then um, from here if you try to derive the estimator, it will be always linear. Okay, and once this is linear, this this will be optimal. Okay, what I'm going to say is that when y bar and x bar are jointly Gaussian, whether you start deriving the Bayesian estimation from this equation, or whether you use such a linear estimator and try to derive the linear estimator, both estimator will be same. Okay, and that will be the optimal one. So I hope you got the clarity. But but usually we consider this to be Gaussian, right? But in practical system we don't know exactly over the air what is happening. I mean, based on certain experiments, it is predicted that okay, this is the channel model which we need to use, and we need to assume the distribution has to be Gaussian and things like that. But it could be some other distribution, who knows, right? There could be some scenarios which could be leading to some kind of other distribution for which the linear MMSE might not be optimal. Okay, in which case some non-linear MMSE could be optimal. Okay, so then then in our system, are we implementing non-optimal estimation? Yeah, there are chances. We don't know under what scenarios it could be non-optimal. But when it becomes non-optimal, we see that the system is having lots of errors, and that is when we declare it as a bad channel condition. And that's why we try to we try to decrease our modulation schemes, or we try to pump in with more power to ensure that channel condition is good, or SNR is good, right? But today we have got AI or ML algorithms, right? So somebody can go to the generic equation of MMSE, which is the expectation of x bar given y bar, and considering the any kind of distribution, if if a nonlinear estimator is derived, and using that nonlinear estimator, if someone can use the machine learning supervised algorithm to train the system using this particular equation for sufficient duration, or for sufficient samples. And then if we allow the system uh, to predict x bar at, then this could be much more optimal than the one which we are using today, which is LMMSE, right? So based on this, there are many research is going on in academia and even in the industry to come up with an optimal algorithm which will work for any kind of distribution, which could even implement a nonlinear MMSE and things like that. So if you can come up with such an algorithm which can be used for 6G, then it will become an IPR, intellectual property rights. Okay, that will become a patent. So if you get a chance, please work on that. Okay, so I think you got the clarity. All right. So if you're looking for more videos like this, please do subscribe to the channel. Appreciate the efforts by subscribing to the channel. Thank you very much. Have a great day. Bye bye.